G'day grade 8s, welcome to our third video in our remote learning sequence here. I do know it says topic 2, I'm just going along with the booklets, on potential energy. So let's get started with our WALT. Here are our two WALTs that we're going to look at. We're going to look at chemical potential energy and how it affects our lives. And then we'll look at elastic potential energy a little bit. Now, the main things that are going to be useful for your assignment will be making sure that you really understand chemical potential energy. There's not going to be much on elastic potential energy in your assignment this term. And you should also know the name of the unit of energy. I may have covered this in the previous video, but a little bit of a recap certainly won't be a problem. So, how energy is stored is really important for you because it allows you to apply that law of thermodynamics that we talked about in our first video, that energy can't be created or destroyed. And so if you can recognize where the energy is kept, where it's stored, that'll help you understand some of those transforms and identify them in your assignments. Now let's have a quick recap. See if you can remember all 10 energy types. Now don't look in your books, try to do it, close your eyes, try to memorize them, think about the way. Remember there are 5 active and 5 potential energies. Now if you've taken a bit of time for this, pause the video, that way I'm not sitting here silently with just some dead screen time. Okay, give it a shot and we'll continue on. So of those 10 types, remember there are potential energies and active energies. Now, I don't really like how some textbooks call it kinetic energies, because to me, kinesis means motion. And if you take physics through to year 11 and 12, there's the study of kinematics, which is the study of things to do with motion. So I like to call it active energies, because these are things that are happening. Yes, they are all examples of stuff moving, but because we're sort of thinking them in the macro state, these big things that we see in our day-to-day life, we're going to call it team active and team potential, okay? Or potential energies and active energies. So those potential energies, remember, were our chemical, our gravitational, elastic, magnetic and nuclear. We talked about gravitational in our last video. And in active we've got kinetic energy, the energy of movement, electrical, sound, light and heat. And they all involve different types of movement, which you'll learn about over a couple of years. So as a reminder, potential energy means something is stored, and active energy is when something is being done. Now, I always like to set little challenges every year. There are plenty of examples where active types of energy are being transformed into other active types. The electricity going through the screen you're watching right now gets turned into light and sound. They're all active types. I want a bit of heat because electronics get hot. But I have not come across any in my readings or thoughts about where a potential energy gets turned into another type of potential energy without going through something intermediate. So I don't know of anything where chemical energy gets turned into gravitational energy without going through something, for example, some motion. The chemical energy stored in my body through my food gets turned into kinetic energy while I lift something up high, which then gives it gravitational energy, but it had an intermediate. So if you can tell me an example, so send an email to me, I'll give you some bonus points on your assignment. And I do this every year. I'm yet to have someone figure one out, but there have been times I've been wrong, and so I'd love it if a student can prove me wrong on this and tell me an example where there is a potential energy that is transformed into another potential energy without having some sort of intermediate. Let me know. So the 3 big ones, at least the big ones we're going to worry about in our unit. Nuclear gets dealt with a little bit in year 9, and magnetic is more for year 11s and 12. So you've got your chemical potential energy, food, batteries, and all types of matter. Gravitational energy, we learned about that last week. Anything that can fall has GPE. And then elastic potential energy, if you can stretch it or compress it, and it goes back to how it was, okay, that's elastic potential energy. So springs are really good examples, rubber bands are good examples as well. Now, science has lots of measurements. One of the real big important mental approach is that we need to measure as much things as possible. So we have a unit for measuring things. If you're asked how tall are you, you might go, oh, I am, say 5'10". That's measuring it in feet and inches. If you're asked how long is a football field, you might go, oh, it's 100 meters. Again, that's the unit. If you're asked how much you weigh, you often give a mass in kilograms. If you're asked how long something took, seconds, minutes, hours, months, years, days. We have lots of different units for time, but there are standard units for science. In science, meters is our standard, kilograms is our standard, and time is measured in seconds as our standard. But energy has its own unit. It's called the Joule. Now, notice the fact that the spelling has a capital J. It's named after a person, so it does get a capital, unlike meters, kilograms, and seconds. Now here's the definition, and this is a really complicated definition. 1 joule is defined as the force needed to accelerate 1 kilogram at 1 meters per second squared over 1 meter of space, which most of you should be going, I don't know what that means. It's a fairly confusing idea. A really easy way for you to understand what a joule is, it's about the energy you need to lift a small apple about a meter. Okay, so not a kilogram. So if you find an apple on the ground and you pick it up, by the time it gets to roughly your waist height, you've gone about a meter. You've used 1 joule of energy. Okay, that's all. That's what it is. So chemical energy, we get our chemical energy from food and liquid. You eat every day. You're hungry because your body needs more energy, needs more nutrients. Our body breaks apart and reforms chemical bonds to store the energy, and that is our day-to-day life. But what happens if we store too much energy? Well, it's a pretty simple process. If we store too much energy, one thing happens, we get fat. That's it. Simple as that. So, how much energy? Now, if you just lay still all day and you do absolutely nothing, like barely blink your eyes, nothing, don't turn your head to watch TV, just get set up so that you can watch TV and do nothing, your body still needs a bit of energy. Your brain needs to work, your heart needs to pump, some basic things need to happen for like your muscles working things through your small intestine. This is called a basal metabolic rate. Okay, and everybody's got a different one. It's roughly, for all you kids out there, about 2,500 kilojoules. Remember K for kilo, so 2,500,000 joules, or 2.5 million joules of energy. That's how much you use just sitting around. Okay, picking up 2.5 million apples every day, just sitting there doing nothing. Okay, and it would be lying down, not sitting up, because sitting up you're going to have to use a little bit of muscle control just to keep yourself upright so you don't fall over. But we need more than that because we don't just lie around all day. Now, for teenagers, for you guys in grade 8, you're going to need roughly 10,000 kilojoules, 10 million joules every day. Boys are a little bit higher because on average you're bigger, and girls need slightly less. Adults like me, we need slightly less again because we're no longer going through growing phases. Okay? Now, there's a great video on this. Have a check it out on the OneDrive. So let's talk about Maccas. I like me some Maccas. How much energy does that give you? How much of your daily energy does it give you from a meal? Now, if you've ever been to a fast food place, you'll often see, oh yeah, you get this burger, but you can get it in a combo, get some chips and a drink with it as well. And you can upsize it. You can go from small to medium to large. Now, I've got an abridged table. You can find these numbers on their website. They are publicly available information. There's nothing there that they're trying to hide. But I'm going to go through some burgers. I'm going to go through some accessories like chips, nuggets, drinks. What I want you to do is identify the energies for the things that you would like to eat. Okay, so if you're going to Macca's and you're going to have a meal, now you might be going, I hate McDonald's, I like Hungry Jack's. Choose something that's about similar, but if you want to make it as authentic as possible, head over to their website. You will find their dietary intake advice. The documents will be a little bit more complicated because you'll be looking at the actual proper document, but the information will be in there. You're just looking for something where it mentions at the heading of kilojoules or joules. So here are some burgers: Big Mac, cheeseburger, McFeast, quarter pounder, McChicken. Like if I go to Hungry Jack's, I quite like their grilled chicken burgers, so I just substitute that for a McChicken and say use that number. It's going to be off by a little bit, different ways of cooking it, different sauces, but at least it's reasonably close. As you can see here, the list, apart from Big Macs and McFeast are pretty high up there. Quarter pounders are a little bit higher. Cheeseburgers are quite low in comparison, and McChickens are a little bit under a Big Mac. So if you like a burger, write down one of those numbers. If you like two of those burgers, write down two of those numbers. If you sort of go, no, I need a lot of food, I need 2 McChickens, write down the number, times it by 2. So there's your burgers. Now, what do you get? Do you get small, medium, or large? Now, if you get a small meal, well, here's your column for your smalls. Small fries, 1,070. Small Coke, 428. Small Coke Zero, 3. Diet Coke, 4. Small chocolate shake, 1,290. Note, that's not a deluxe chocolate shake, that's just a regular chocolate shake. And frozen Cokes down there as well. Now, if you like, if you're not a burger person, you like chicken nuggets, well, here's the energy for 1 chicken nugget. Multiply it by your pack size. You like 6, multiply by 6, like 10. Slap a 0 on the end of it. You go for 20s, double it, then slap a 0 on the end of it, or just multiply it by 20. Okay. And figure out how much is your total energy from this food. Other things you might like to do is to take that total energy and divide it by the 10,000 kilojoules that you need on a given day, and work out, well, how much of your daily energy does eating one meal at McDonald's give you. You'll find that it does give quite a chunk. So chemical energy is not just in food though, it's also stored in other types of chemical bonds. And in order to use energy for ourselves and for the machines around us, like our cars, we need to make and break those chemical bonds. Batteries, your little, from all the way down to those little single cell batteries that you find in watches, through to the batteries in the back of your remote, and up to batteries in your car. These are chemical potential energy sources. The petrol we pump in, chemical potential sources. Okay, all fuels are chemical energy. It's very, very easy, which is why we are so reliant on it, that the fact that we can burn it and get so much energy out of it for so little investment nowadays, that makes it so used by everything around us. But it is pretty dirty. We are kind of lucky living in the time we are right now, in that we can see, well, what happens if everyone just stops using cars? What happens to air quality? And we are seeing that air quality has been clearing up quite a lot very, very quickly. For once, China didn't have a huge cloud of pollution over it when they were in the middle of a lockdown, and their manufacturing stuff was turned off because they weren't burning these easy fuels. We're going to have a look at pollution in a later unit this year, so we'll be coming back to that a little bit later on. But for now, we can just think of it as, it's a very easy source of energy. The way we often use it is that we use chemical energy to convert to heat, or sometimes electrical energy. We can use heat to boil water, and that steam turns a big fan, which creates kinetic energy, and then that allows creation of electrical energy in power plants. That's how coal power plants work. But again, we'll look at power plants in a little bit more depth when we do our use of energy stuff. Okay? So let's look at our other type of energy, elastic potential energy. Now, you might not have a person to brainstorm with, unfortunately, but try to think about some springs. What are some springs you've seen around your day-to-day life? What could make them more or less springy than other springs you've seen? Give it a moment and we'll come back together. Okay, you might sort of think, well, what about the size of the spring? Is it longer? Is it shorter? What about how thick the coils are? Is it a really thin metal? Is it a really thick metal? What about how round it is, if it's got a very small diameter versus a very large diameter? So there's a lot of physical properties, and what we make it out of is pretty important as well. Might also say the same thing for elastic energy. I'm pretty sure most of you would state quite comfortably that not all rubber bands are the same. That different ones stretch different amounts. Some you've got to pull hard, some you've got to pull short, some are quite large, some are quite small. So physical properties go a lot into different how much elastic energy something can store. So for springs and rubber bands, two properties. The first thing that matters is displacement, how far we stretch the rubber band. If you stretch it more, you've put more energy into it. The second thing is pretty straightforward. It's called a spring constant, and every spring and rubber band has its own spring constant, and most of the time you have to work it out just by testing on it. There are some models that allow you to predict about what it would be, but generally you just have to go, you get a spring, you make it, and you just go do some testing on it, and you go, okay, this is about the constant for this thing, which is something we do in senior physics. So, home experiment time. Kids, this is the moment you've been waiting for, the chance to flick rubber bands around and be told it's for science. So, what you're going to need? A ruler and some sort of elastic band, rubber band, hair tie that you've pinched off your sister, your mother, or your long-haired brother or uncle, something that you can stretch and flick, and you're going to need a ruler. Now, if you don't have a ruler, you can make one. You just need something that's a little bit firm that you will be able to hook a rubber band onto, and I'll show you what I mean by that in a second, and mark off some consistent marks on it. Use a thumb width. Doesn't matter if you don't have, like if they're not all centimetres, or they're not all inches, or they're not all millimetres. What matters is that they're consistent. So if you need to go, look, it was 5 of my thumb widths, I stretched it, and it went 10 of my foot lengths, that's perfectly fine. Just make sure that you're being consistent with how you measure. Keep things the same. So your method's pretty easy. You're going to hook the rubber band over the end of the ruler and pull it back to a fixed number. Now, just like here in the picture, so you can see here it's hooked over the ruler, and they've pulled it back. Here's gone all the way up towards 20. You're going to have to figure out what your first number is, because obviously I don't know what your rubber band looks like. 10 centimetres might work for you. 5 centimetres might work for you. You might have to go to 15. I don't know, but you just find something that gives you a stretch. Don't go all the way to the end, because you're going to have to do a few different lengths and save going all the way to the end until your last one. You definitely want to do that one, but don't start there. Start with some of the smaller ones and build up to the big one. Second thing you're going to do is aim it and release it. Try to aim horizontally. Okay, so don't point it up at a let's see. I'm going to have to draw it here. So if you're here with your thing, don't point your ruler up here so that your thing goes there. You want it to be horizontal so that it comes out from you and falls straight down. If you are going to do it at an angle, you'll just have to make sure that you get the same angle every time. Okay, that's the important bit, that you've got to keep things the same as much as possible. And I want you to do it a couple of times. 3 is pretty good to start off with. If you want to do more, do more. Don't let me hold you back on that, but at least 3. Okay, so you're going to pull back, pull to the same distance, shoot, measure how far it goes. And remember, in the wise words of Adam Savage, if we're not writing it down, we're just screwing around, write your numbers down on a table, and then do the same thing for some other stretch distances. And I've made an example table here, so you'll need a column for stretch. I've got here 10, 15 and 20, but your numbers will depend on your stretchiness. Trial 1, trial 2, trial 3. Here's some examples. Maybe trial 1 goes 1.1 metre, 1.2, 1.2 metres, and then average them. Remember to average, add up your numbers, divide by the number of trials. If you do 3, I'd go 1.1 plus 1.2 plus 1.2, add them up, which would be 3.5, and then divide that by 3, and you'll get about 1.6, no, not 1.67, 1.167. Ooh, Let's fix that up. 1.167. Oops. Can't get a number bigger than what you started with. That was a silly mistake of me. If you got, 2, 2 and 2, well, that's a nice easy average. Your answer would be 2. If you did 5 trials, you'd add them all up and divide by 5. Okay. And then after you've got that, here's a couple of questions for you. Yeah. What happened to the distance, how far it went, as you stretched the rubber band more? Were your trials consistent? And remember, consistent means, did you try to make them the same as possible, or did they vary a lot? And that means, so if you're first, like if I go back to here, these are roughly consistent. I mean, 1.1 and 1.2 are a little bit different, but I'm dealing with a rubber band being shot through the air. Okay, it's not going to be ideal every time. If the first one was if I go and say fill in some numbers here and go, well, this one could be 1.3, this one could be 2.9, and this one could be 2.7. Okay, well, these two are pretty close, but this one's not, so that's not consistent. Is this one the weird one, or did something weird happen to make these two go further? Did I do something different? Okay. Now, and the last one, without changing your stretch length, how far you've pulled the rubber band, what could you change to make the rubber band go further? Okay. There's a few different answers. It'd be interesting to see what you guys think about. Alright, so this covers the stuff for week 3, okay, on potential energies. Keep working hard, email your teachers if you've got any questions, and stay safe. Thanks, guys.